Greetings everyone. Today I'll be discussing about the latest geomechanical problems in underground mines and the usefulness of geomechanics laboratory in solving the problems as a part of my assignment for the geomechanics laboratory. So, in mining, going deeper, increasing safety standards and aiming for higher productivity demands engineering to maximize these values. Lack of engineering for constructability when tunneling in weak or brittle rocks at depth often leads to unnecessary cost and involves a lot number of accidents. Usually in underground coal mines, there are a number of fatal accidents that have occurred due to roof fall. The roof fall mainly occurs in the newly exposed working sections of coal mines during development as well as during the final extraction of coal, that is during depillering. The main factor which contributes to such roof failures in the coal mines is the redistribution of stresses and the geotechnical discontinuity. If we have a proper system design, it is within a proper time, then the layers won't get detached and the fall might not occur. And for such system, we need a proper roof failure tracking mechanism so that we can know and track when the roof fails and can design proper supporting system accordingly. So, what are the latest geomechanical problems of the underground coal mines? These include the lack of continuum properties of the rock. The lack of continuum properties of the rock means that since these rocks are comprised of large number of potential discontinuities and have bound potential and are of different size and orientation, location, it becomes very difficult for us to measure these parameters. The forces or the stresses acting on these large volume of rock masses. These forces or stresses which are acting are completely variable and change from point to point. Hence, we can use the point measurement technique in order to measure the rock stress as much as possible. The strength of the rock mass is also not yet known, and there are no particular formulas or derivations through which we can determine the strength of the rock mass. All those formulas which are there also depends upon the mining conditions as well as the depth for which we are mining. The time dependent behavior of the rock mass. The rock tends to change its property, that is the porous nature, the brittleness and the continuous property as well. They all tend to change with time. The blast damage due to the rock mass, particularly from large scale blasting operations, also tend to have a factor of safety which we cannot easily calculate by a particular formula, and hence we need the application of the geomechanics laboratory here so that we can determine the properties of the rock by using a sample which we gather by core drilling or any other method. The sixth one is the issue of reducing the in situ stress measurement, which include since there is no particular derivation for the measurement of in situ stresses, as they are not particularly available with a lot of data. Hence, it becomes difficult for us to calculate the in situ stresses. Then we have the failure criteria suitable for the rock. Since all these rocks are completely different as per their properties, it becomes difficult for us to determine the failure criteria of the rock, and it can only be determined by using the geomechanical properties of the rock. So, how do we utilize the geomechanical lab for solving such problems? The geomechanics lab has a very important role to play in assessing the formation integrity during well construction and completing of mining processes, and in response of the reservoir to oil production, water injection and depletion. This course not only provided us with details of all the tests which are most commonly used to determine the fundamental rock mechanics parameters, which include the strength index characteristics, compressive and tensile strength, elastic properties which include the Young's modulus, Poisson's ratio, etc., rock failure parameters like Moore-Coulomb circle, cohesive strength, etc., but also the in situ stress determination. The applications of the geomechanics laboratory can be found in a lot number of places, which include estimating the rock mass strength from laboratory properties for the slope stability design, high wall mining pillar design, evaluating valley closure subsidence, optimizing the cable bolt performance in varying geotechnical environments, and design of support system and stability of the underground workings. Here, I will be discussing about the design of support system as well as optimizing the cable bolt performance in the geotechnical environment. ground. The geotechnical lab data can be used to improve the design and the performance and reliability of strata control system for the benefit of the underground coal mining industry. It can result into a series of practical outcomes, including the establishment of new axial load test facility and procedure to test the cable bolts currently used in the mine. For the design of the support system, we can use the numerical modeling method in order to determine the factor of safety and the strength and the resistance that needs to be provided to the roof, so that the roof doesn't fall and there are less number of accidents that might occur in the underground mines. So, let me discuss about the design of support system and the stability evaluation for the underground workings. Generally, in the underground coal mines, there are a number of fatal accidents that have occurred due to roof fall. The roof fall actually occurs for the newly exposed working sections, as well as at the same time it involves the depillaring section too. The main factor which contributes to such kind of a roof failure is the redistribution of stresses and geotechnical discontinuities, as I have discussed earlier. So, if we have a proper support system, then it can help the layers to not get detached and fall, and which might cause casualty in the mines. The rock mass rating here plays an important role in design and selection of adequate support system. In the Indian coal mines, Central Mining Research Institute Indian School of Mines rock mass rating has been referred to as CMRI ISM RMR and is mostly used for formulating the design guidelines for support systems. The accident due to roof fall constitutes the major challenge faced by the field engineer. Thus, proper care should be taken to increase the stability of the working by characterizing the roof falls and also execution of a proper mining plan to arrest the movement of the layered strata which are liable to fall when the stresses acts upon them. You might be thinking that why am I talking about detachment? The detachment that here I am talking about is basically bed separation that occurs when these layers tends to get decombined due to the forces which are acting due to the gravity, and sometimes due to the heavy working that is going on in the underground mines, which include the heavy machineries. I have taken here a case study here which belongs to Gair Palma mines of Raigarh coalfields, Chhattisgarh. We have considered the fourth seam, the second seam of the fourth panel, and the seam 3. The thickness of the second seam is 2.5 meter and the thickness of the third seam is 4.5 to 10.23 meter. So we might say that the third seam is slightly thicker than the second seam. The width of the gallery is 4.8 meter in both the seams, and the height of the galleries are 2.5 for the top seam and 3 meters for the third seam. Pillars as prescribed by DGMS are 25 into 25 and 36 into 36 center to center, and depth of the cover is 30 to 160 meter. Since it is prescribed by DGMS to follow a particular rule, hence the case study also belongs to the same, and we are taking only the pillar size as described by the DGMS. As you can see in the figure, this is the virgin coal pillar that has been described here with a 2.5 meter coal seam, that is the second seam, and the immediate roof which consists of the sandstone for the second seam. The immediate roof of the second seam is sandstone, as I described earlier, and there are random joints that have been discovered. The average layer thickness of the sandstone is 8 centimeter, and there's a percolation of water. So we now know that while considering the RMR, we have to consider the groundwater and weatherability as a factor because of water percolation in the rock. The compressive strength of sandstone is 110 kg per centimeter square, and the density is 2.1 tons per meter cube. And the first cycle of slake durability index of sandstone is 88.7. This first cycle of slake durability index can be calculated by taking the coal sample and performing the slake durability index test which we have already performed in our laboratory. The RMR of the immediate roof for the second seam was found to be 46%, and with adjustment it was found to be 41.4. Here the 10% adjustment that we are taking is because of solid blasting that is happening below the ground. Then you might be thinking, how did we calculate the RMR? The RMR is calculated by the formula that is prescribed by CMRI ISM, and we have considered the layer thickness as 8 centimeter and given a rating of 40 14, structural features joint with a rating of 10, weatherability with a rating of 10 because it is 88.7% due to the percolation of water, compressive strength as it was given is 110 kg per centimeter square, that is for sandstone, and the rating is 3. The fifth factor that we have considered is groundwater. Since there's a percolation of water and it is the roof surface is quite moist, we have taken the rating as 9. So how did we calculate the rock load? The rock load for the gallery and the junctions have different formulas as prescribed by DGMS or Buoyancy, you might say, because the same formula is taken everywhere. So it is basically B into D into 1.7 minus 0.037 RMR plus 2 into 10 power minus 4 RMR square for the galleries, and for the junction it is 5 into B power 0.3 into D into 1 minus RMR by 100 whole square. Here the B that we are considering is rock load width, and the D we are considering is the dry density, that is 2.1 tons per meter cube. So by this formula we calculated the rock load for galleries and the rock load height for galleries and also the junctions. So we got that the rock load for galleries was 5.15 tons per meter square, and the height for rock load height for galleries is 2.45 meter, and the rock load for junctions was 5.76 ton per meter square, and rock load height for the junctions was 2.73 meter square. There has been a relationship which has been established for horizontal in situ stress in order to determine the in situ stress, which I told was unmeasurable, but there are some relationships which are available by various scientific researchers and they have tend to proved it correct for some of the coal mines. Here we have used for the calculation of vertical in situ stress a normal formula, that is 0.027 into H. H is the height of the depth of the seam, or which we have taken as 160 meter, and the horizontal in situ stress is calculated by 2 plus 0.1 into 10 power minus 2 into depth of the mine or depth of the seam. So post we calculated the horizontal and vertical in situ stress, it becomes very necessary for us to go for numerical modeling, as numerical modeling can help us to give a comparative result between the theoretical values that we got and the processed values that we might get for designing of the support system. As you can see in the figure, 2.5 meter is the extraction height for the second seam, and the area which is extracted is vacated in the figure. This was previously this is the virgin model. It hasn't been processed yet. It's just shown that there is a 2.5 meter extraction that has been done. As you can we involve for the numerical modeling process, we involve 3 stages. First is the virgin model with the elastic constant density, in situ stress boundary conditions and other parameters. The third stage includes extracted model with drivage of 4.8 meter and 2.5 meter for the second top seam. The third one is the evaluation of the safety factor for galleries and junctions and for estimating the rock load height in order to prescribe a particular support system for the mines. So, as you can see in the figure, the red region indicates high in situ stresses, both vertical and horizontal, whereas the green region indicates that there is comparatively less stress acting on the roof. The blue region shows that we have to design a support system for this particular 2 meter height of the junction. The rest of the yellow region shows us about the discontinuity that exists in the rock. The safety features, the safety factors that the contours obtained for the second seam was less than 1 meter. That is, it needs a strong support system which might consist of cable bolts or any other or resin bolts or resin or grouted cable bolts. It depends upon the height, which has been found to be 1.5 meter, and the rock load obtained for galleries and junctions was 3.15 ton per meter square and 4.2 tons per meter square. For designing, since we had the numerical model already designed, so we can easily design a support system for the gallery. The gallery was supported with 4 bolts in a row at an interval of 1.2 meter, leaving the 0.6 meter spaces towards the pillar on both the sides to act as ground pillars, and the bolting rows were spaced at 1.2 meter. The 2 side bolts is inclined at an angle of 600 towards the 60 degrees towards the pillar, and 2 central bolts were grouted vertically. The bolt length is 1.8 meter and the diameter was kept to about 20 to 22 meter and made up of TMT ribbed bar, and the whole suggested diameter was did not exceed 32 millimeter. All the bolts were grouted with full column resin capsules, and the bolts were tightened immediately along with bearing plates and nut so that they don't suffer any kind of bed separation. The support resistance which was offered by the support system was about 10.41 ton per meter square, which provides us a safety factor of 2 considering the 15 ton load bearing capacity of each of these bolts. These bolts were made up to a length of 15 meter inside the roof. The support resistance that we calculated by the formula of number of roof bolts into anchorage divided by the width of the gallery into row spacing, we got it as 10.41 meter square, and as described earlier, the safety factor was 2. As you can see, earlier the safety factor that we calculated for the pillars was less than 1. So after having the cable boards grouted inside the roof, we know now we got the safety factor as 2. So this is how we can examine that how a support system will help to prevent the number of accidents that have been occurring in the mine and can help our workers to have a safe operations inside it. For the junctions, the rock load at the junction was 5.76 ton, and the junction was supported with 4 bolts in a row at 1.2 meter interval, along with the row spaced at 1.2 meter, and there were 5 rows consisting of 20 bolts, and at a junction of 4.8 into 4.8 meters. The safety factor that we got here was 2.26, you might say 2.3, and the support resistance was 13.02 tons per meter square. So here also we can see that how the safety factor for the after having the cable bolts at the junction has changed and has become a lot more supportive than it was. This is just a figurative description of what I said earlier. As you can see, the bolts, the 2 end bolts are at 0.6 meter distance, inclined at an angle of 60 degrees. These are left for the crown pillar, the 0.6 meter and 0.6 meter. The rest of the bolts are at a distance of 1.2 meter and are vertically upheld. The panel section has been described as 4.8 meter, and the panel is 4.8 meter into 4.8 meter with 2 of the grouting at 1.2 meter. As you can see, the bearing plate is also attached to it as soon as the bolts were fitted into the roof. Finally, I would like to say that there should be a clear identification of the processes and the laws that describe the failure in the geomaterials, and it's a central part of the successful practice of geomechanics. So there's a notion of failure that can take different interpretations depending upon the type of geomaterial and its current state, as categorized by the stress state and stress history, but it is equally applied to geohazard identification and mitigation. There are other valuable applications of the technology too in the mining industry. In order to bridge the gap and expand our knowledge to cope up with the current challenges, it requires a new thinking which we can get by this laboratory. I would like to thank Professor S. Jayantu for taking our lab even via online method during this COVID-19 pandemic, and I would like to thank him for giving me the opportunity of explaining about what I have learned through the geomechanics course. And last but not the least, I want to say that lessons learned from science always indicate the path of developing solutions in mines via geomechanics peripheral research. These are my references that I have used for preparing this presentation, and thank you.